Good afternoon. I'm Professor Sever. Today we're going to do an introduction to abstract vector spaces and subspaces. Again, the concept of linear combination is similar to that in the Euclidean space, and it's the direct analog. Now here I'm writing the scalar plus and the scalar times and the scalar plus to illustrate that these are abstract operations. Eventually, after we become familiar with it, we'll write again the scalar times as concatenation. We would write it as just C1 V1, and we would write this circle plus as just plus. But for now, since we're exploring new, potentially abstract operations, I'm illustrating that these are not necessarily the classical operations of plus and multiplication that we're familiar with. A linear combination of the vectors v1 through vk is what you would think it would be. It would be a multiple of v1 plus a multiple of v2, and so on, keep adding until you add a multiple of vk, where the ci's are scalars or real numbers. So let's look at the following theorem or proposition. Again, this could be proven, and this is the motivation for the axioms. Notice I said we have the zero vector is unique. Again, if we were doing this at a higher level, if this was a senior level course, what we would say is there is a zero vector z such that u plus z is u for all u, and then we would prove that z is unique. Okay, and again in this analog we would say there is for each u in v there is a y such that u plus y is 0, and then we would show that y is unique, and therefore we would then adopt this notation of minus u for it. It wouldn't make sense to adopt a minus u if there were two different objects that had that property, but there aren't. There's just one. Okay, so the proposition, zero vector is uniquely determined, which means there's just one of them. It's unique. Cancellation, this is nice. If v, y, and z are vectors, then y plus v equal z plus v implies y is equal to z. In other words, look, you can cancel the v. We would say subtract v from both sides, and that's in fact how you would prove that. That's a way to prove it in terms of thinking about things operationally. And finally, axiom 5, the additive inverse minus u is unique. Again, there's just one of them. For each u, there's only one vector in the vector space that you can add to it and get the zero vector as a result. So once again, we have another analog of the definition of subspace in Euclidean space. So let's state that. A subspace W of a vector space V is a subspace of V, which is a vector space in its own right. In other words, it's a vector space with respect to those 10 operations. So if V is a vector space, a subset W is a subspace of V if it has these three properties. First, it has to be non-empty, so it has to have something in it. W is closed under scalar multiplication, and W is closed under addition. So these are actually 3 of the 10. So what happens is if you have these 3, then you can prove that the other 7 properties hold. Some would be directly inherited. If u plus v is v plus u for all vectors v, then of course that has to happen for any vectors in a subset of v, right? That property would be inherited from v. The associativity is inherited. Now the ones that aren't inherited are the closure, the zero, the additive inverse, scalar multiplication. These are inherited, 7, 8, and 9, and of course 1 would be inherited as well. So in that sense, we only need to check 3 things. For a subspace determination, if you're looking at a subspace W, if you know W lives in a known vector space and you want to show W is a vector space in its own right, namely a subspace of V, you only need to show 3 things instead of the 10 vector space axioms which comprise the definition. And in fact, you can combine 2 and 3 together and show those simultaneously if one wanted. So let's look at another theorem. Subspace W of a vector space V is a subspace of V if and only if, and this is a reformulation of the last statement. Instead of saying it's non-empty, it says, okay, the zero vector is in W. So if the zero vector is in there, certainly it's non-empty. W is closed under addition, and W is closed under scalar products. That's precisely what these two statements were saying. Here, instead of just saying generally it's not empty, then we've converted to say the zero vectors in W. Examples of well-known vector spaces. Obviously, we spent a lot of the semester studying Rn. We've looked at that polynomial space Pn. Sometimes I write that as Pn of t. I've written it a little bit differently today. Then the set M, capital M, Mn. The capital M stands for matrices. Little m and little n stand for the size or the dimensions of the matrix. So this is the set of all matrices that are m by n, which I've got written here. P stands for polynomial space. N stands for the degree. C stands for continuous functions on the closed interval AB. This is a nice calculus-based example that the continuous functions on the closed interval AB form a vector space. So let's look at the following space in the plane. So we have W as the set of all ordered pairs that are on the line y equal mx. Then let's look at the set of all ordered pairs such that y equal mx. Then W is simply a straight line through the origin. We know that. So now, is the origin 0, 0 in W? That's one of the questions we have to ask. Recall, we just said we can prove, if we can prove these three things, I can show W is a vector space or W is a subspace of V. So I need to show that the zero vector is in W. I need to show that scalar multiplication is closed in W. And I need to show addition of vectors is closed in W. So let's look at that. Is 0, 0 in there? Sure. For any m, what's m times 0? 0. So if x is 0, y is 0, that says the ordered pair 0, 0 satisfies this equation, therefore 0's in W. So let's look at scalar multiplication. Now scalar multiplication is defined as coordinate-wise multiplication. So if xy is in W, we need to show that c times xy, the ordered pair xy, is in W for any choice of c. Well, let's look at that. So what does it mean for cx, cy to be in W? It would mean that cy is equal to m times cx, which it is. Hence, the ordered pair cx, cy satisfies this equation. Therefore, cx times y is in W. Therefore, scalar multiplication is closed. Another way you can envision this, and this is the way I'm kind of doing it on the proof, it's proving it a little bit reverse. Suppose xy is in W, therefore y is equal to mx for that fixed m. Multiply both sides by c, therefore c times y is c times mx. Now we can commute the m and the c as real numbers, which is the same. That means this product is the same as m times cx. Now we have it that cx comma cy satisfies the equation, therefore xy is in W. We get the similar result for vector addition. So if x1, y1 is in W and x2, y2 are in W, then we know that x1, y1 satisfies this equation. The same holds for x2, y2. That tells us y1 is m times x1, y2 is m times x2. We add coordinate-wise, and now we know that y1 is m times x1. We know y2 is m times x2. y1 plus y2 is mx1 plus mx2. Factor the m's. So now y1 plus y2 is m times quantity x1 plus x2. Therefore, the ordered pair x1 plus x2, comma y1 plus y2 satisfies this equation. Therefore, it's in W, and it is the sum of the two original ordered pairs. So therefore, we've done it. W is a subspace of R2. So let's take a closer look at one portion of that previous theorem. The theorem said that W was a subspace of V if and only if three conditions happened, the first of which was the zero vector is in W. So I just want to look at that. Now remember, we didn't prove that theorem in this last demonstration. We used it. I would like to prove the first statement, namely, if W is a subspace of V, then the 0 vector has to be in W. If we could prove that, that would give us the corollary that if 0 is not in W, then W could not be a vector subspace. Let's run through the proof. Suppose W is a subspace of a known vector space V. Now, because W is non-empty, there must be something in it. There must be some element, let's call it little w, in cap W. Now, because W is closed under scalar multiplication, why? Because it's a vector space, then it must be the case that any scalar times little w must also be in W. That's the closure of the scalar multiplication, the closure of the scalar product. So what if we chose the number 0? So 0 is a real number, so 0 times little w would have to be in W because W is closed under the scalar product. But we've already proven that 0 times any vector is the 0 vector. Thus, we would see that the 0 vector is in W because the 0 vector is equal to 0 times little w, and 0 times little w is in the vector space W. The proof is complete. Let's take a look at our corollary. Conversely, if 0 is not in W, then it can't be a vector subspace of V. Thank you for watching the third part in this video series on an introduction into vector spaces and vector subspaces. I'm Professor Sever. Thank you. In part 4 of this video series, we will discuss a general plan or technique for showing that a subspace is a vector subspace, and we will look at a calculus-based, concrete, or well-known example of a vector space.